Hey guys, I'm Jade. Today is my LeetCode review vlog on 129th problem, some root-to-leaf numbers. We are given the root of a binary tree containing digits from 0 to 9 only. And for each root-to-leaf path in the tree represents a number. For example, the root-to-leaf path 1 points to 2 points to 3 represents the number 123. We have to return the total sum of our root-to-leaf numbers. Test cases are generated so that the answer would fit in our 32-bit integer. And a leaf node is a node with no children. Let's see example 1 here to understand this problem easily. We got a binary tree here, root node 1, left node 2, and right node 3. So the explanation is the root-to-leaf path 1 points to 2 represents the number 12. The root-to-leaf path 1 points to 3 represents the number 13. We add them together, we got 25 here. So the output is 25. Then let's get started with our intuition and the idea to solve the problem. And there are 3 steps to solve this problem. First, we need to traverse the binary tree to visit all root-to-leaf paths, and there are multiple ways to traverse the binary tree. For example, depth traverse the binary tree using depth first search or breadth first search. For depth first search, we can do it by recursively or iteratively using a stack. And for breadth first search, we're using a queue to traverse the tree level by level. And the second step, when we traverse the root-to-leaf path, we will compute the new number by multiplying the current number by 10 and adding the value of the current node, which is compute the new number of current path. This is the second step. And for the final step, when we reach a leaf node, the number formed by this path from root to this leaf node should be added to the total sum. Add all root to leaf number. Then let's get started first by the depth first search recursively. We'll use the recursion feature to traverse the tree and get the final sum. Then let's get started with the code. First, we have to create an extra function method to help us solve the problem, to do a recursion. Let's say private integer, let's call it depth first search, and this method will take 2 parameters. First is a tree node, and the second parameter should be the current sum. And inside the sum numbers, we have to call the DFS method, DFS, with root node and the initialized sum, which is 0. And inside the DFS method, first we have to check for the bad case. If the node is null, then we just return 0, as there is no path to sum. If node equals null, then we'll return 0. Second, we'll update the current sum by multiplying the previous sum by 10 and adding the node's current value. Current sum equals current sum multiply 10 and plus node dot value. Then we have to check if we reach a leaf node. If so, we'll return the current sum as this is the past sum. If node.left equals null and node.right equals null, then you just return the current sum. Or if the node is not a leaf node, then we'll recursively calculate the sum for the left subtree and right subtree if they exist, and return the total sum. And the code is return, and we have to recursively call that first search with the subtree, left subtree and right subtree, node.left with the new current sum, and that first search with node.right with the new current sum. And that's all of the code. Let's submit code and check for the correctness, and then analyze time and space complexity. Yes, our code got accepted. So for the time complexity, it should be big O of n. And n stands for the number of nodes in the binary tree. This is because we have visited each node in the tree for only one time, and the space complexity depends on the depth of the binary tree, which can be big O of h, and h stands for the height of the binary tree. In the worst case, for example, if the binary tree is a skewed tree, the space complexity could be big O of n. But if the tree is a balanced binary tree, the space complexity could be big O of log n due to the recurrent depth. And this is the first approach. Then let's come into the second approach. So for the second approach, we could create an explicit stack to simulate the depth first search traversal. And for each element in the stack contains both a reference to the node and the current path sum formed up to that node. Then let's get started. The very first step, we still have to check for the bad case. If root equals null, then we just return 0. And the second step, we'll create an extra empty new stack to simulate the depth first search feature. And each element contains a pair of node and current path sum. Let's create a stack of pair of 3 nodes and an integer. Let's call it stack equals new stack. And then we have to push the root nodes and initialized sum into the stack. Stack.push of new pair with the root nodes and initialize sum 0. And then we also have to create an extra member, integer total sum, starting at 0. Then we'll create a while loop to traverse the binary tree with a stack to simulate the depth first search. While now symbol stack dot is empty. which means if the stack is not empty, we'll continue this while loop. And for each iteration, first we'll pop up a pair from the stack to check if the node is a leaf node and update the current path sum. So we'll create a pair member, pair of tree nodes, and integer. Let's call it pair. So we got pair from the stack.pop. Then we have to get the current node and corresponding current sum. Tree node equals pair dot get key and integer current sum equals pair dot get value. Then we have to update the current path sum by multiplying by 10 and adding the node dot value. Current sum equals current sum multiply 10 and plus node dot value. Then we have to check if the node is a leaf node. If so, we'll add the current sum into the total sum. If node dot left equals null and node dot right equals null too. Oops. If so, we'll add the current sum into the total sum. And the total sum is the answer that we are chasing for, total sum, with the new current sum. But if the node is not a leaf node, then we'll push the right and left subtree into the stack if they exist. And there's one thing we can remember. We can push the right subtree first. So the left subtree would be processed first in the stack due to the last in, first out feature of stack. And this step could obey the sequence of pre-order traversal. So let's check the right subtree first and push into the stack. If node dot right is not equal to null, then we'll late stack dot push with a new pair with node dot right and a new current sum. And then we also have to do the similar process to the left subtree is not equal to null. Then we'll call stack.push with a new pair, node.left with new current sum. And out of the while loop, we just return the total sum of all the root to leaf paths. Return total sum. Then let's submit code to check for the correctness and analyze the time and space complexity. Yes, our second approach code got accepted again. So the time complexity, it is still big O of n, as we visit each node in the binary tree exactly once. But the space complexity is big O of n. This is because in the worst case, for example, a balanced tree or a skewed tree, we could hold all the nodes during the traversal. And that's the second method. Then let's come into the final method, breadth first search, using a queue. So we can also solve this problem using the BFS. And the detail is we'll use a queue, which each element in the queue stores both the nodes and the current sum. And we'll process each level of the tree and update the sum at each node. And when we reach a leaf node, then we'll add the current sum into the source of sum, which sums very similarly. Then, let's get started with the final approach. Is right here. So for the third method, the first state is very similar. We have to check for that case. If root is equal to null, then we'll return 0. And then we'll create a queue to store pairs of node and corresponding current sum. Queue of pair of tree node and integer. That's called queue, and assign a new linked list, which is an implementation of the abstract queue class. New linked list to the queue member, queue variable. And then we'll push a new pair, which is the root node, and initialize sum 0 into the queue. The code is queue.offer of a new pair of root node and initialize sum 0. And then we also create an extra variables called total sum to store all the root to leaf path sum, total sum, starting at 0. Then we'll create a while loop traverse the tree level by level with a now symbol queue.is empty. If the queue is not empty, we won't stop this while loop. And for each iteration, we'll dequeue the front element from the queue first. And the code is pair of tree node and integer. That's called pair equals queue.poll. And then we have to get the tree node, the current node. Node equals pair dot get key and the current sum of this path. Current sum equals pair dot get value. And then we'll have to update the current sum by multiplying 10 and plus node.value. Current sum. Current sum equals current sum plus 10 multiply 10 and plus node.value. And then we'll check if the node is the leaf node. Node.left equals now and node.right equals now. If so, we'll add the current sum into the total sum. But if the node is not a leaf node, then we'll enqueue the left subtree and the right subtree into the queue if they exist. And we can enqueue the left subtree first, so we can obey the sequence of pre-order traversal. Root first, then the left subtree and the right subtree. So we have to enqueue the left, but we have to check if node.left is not equal to null. If so, then we'll enqueue the new pair of the left subtree and corresponding current sum. Queue.offer of node.left and corresponding current sum. And then we have to do the same to the right subtree. If right subtree is not now, then oops, I forgot to create a new pair here. New pair. For the right subtree, If it's not now, then we'll call q.offer of a new pair with no.write and curly sign to prepare for the next iteration. And out of the while loop, we just return the total sign. Then let's submit code and check for the correctness and analyze time and space complexity. Yes, our final method code has been accepted. So the time complexity is still big O of n as we process each node for only one time. And the space complexity, it is big O of n too, because in the worst case, for example, a balanced binary tree, we could store up to n over 2 nodes. Oops. We could store up to n over 2 nodes in the queue. So during the traversal, so the space complexity, it is big O of n. And that's all of my LeetCode review blog for this problem. And I highly recommend you guys to visit my online GitHub page here, which contains all the nodes and codes, explanation, and the time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page. And I'll put those two links on my YouTube description below. Sorry, the network is not stable. And thank you guys for watching, and I'll see you next time. Bye bye.